Okay, hello everybody. My name's Simon Prickett. I am the developer advocate manager at Redis, which is a company that makes something that you may know of as a cache. It fits into the previous talk because it's really a database that a lot of people actually use as a cache. So today we're going to talk about doing something different with Redis that isn't the caching or the session store that you might have seen before. We're going to use it to count things, and we're going to be wrong sometimes. And you might think, oh, that's terrible. The product must be awful. It can't count things. So we're going to look at why sometimes it's OK to be wrong when we're counting things. So let me try this. There we go. It works. So we want to count things. This is a fairly simple problem on the face of it. But as with a lot of things, when you start to look at something, it can be as complicated as you want to make it. So when we're counting things, that's pretty easy. The problem comes when we want to count distinct things. So imagine all of these sheep here have some sort of unique identifier. It's usually a tag in their ear. And that tells us which particular sheep this is, and that's used for sort of inventory management, what vaccines it has, all sorts of things. Lots and lots of things have these sorts of things. So warehouse inventory, vehicles have license plates, aircraft have registrations. We need to know, in some cases, both how many of something do we have and which particular ones have we seen before. So we're going to use sheep as it's a fairly common counting metaphor. So this is a Python conference, so we're going to look at this in Python. And in Python, one way we could determine how many distinct things we've seen is using a set, which is a built-in data structure. So it's fairly easy. We just declare a set. We add a load of unique things to it. It behaves like a mathematical set, so it will deduplicate those things. If we add like 1934 a couple of times, it will only appear once in the set. And then we can say to it, how many things have we seen? What's the length of that set? And it's going to be right all the time. It's going to tell us how many distinctly different things we've seen. So easy. We can do that in Python, no problem at all. So then the other question we want to ask when we're looking at counting distinct things is, have I seen this particular unique identifier before? So have I seen this sheep before? Again, a Python set looks like a really good idea for this because I can put all the things in the Python set. It deduplicates them for me. As we've seen, I can see how many there are. And then I can say, oh, have I seen a particular sheep? So is some ID in the set of sheep ID that I've seen before? And it's going to say, yes, it is, or no, it isn't. And it's going to be right 100% of the time, always. So that's great. And we've spent about 6 minutes and we're done, right? We've counted everything. So we've counted how many, and we've counted, we've seen if we can see a distinct sheep. And the Python set is absolutely perfect for this. But is it? So why would that not be the case? Well, we tend to have lots and lots of things. So counting a few things, that's OK. We can do it in memory in one process. And we won't blow out the memory on the machine that we're using. And we don't need to worry too much about persistence or recoverability or anything like that. For a simple case, sure, it's fine. When we get lots and lots of things, and we can go big in 2 dimensions. So we could have many, many sheep or many, many IDs. Or the actual unique identifiers themselves could become really big. So a unique identifier might, for example, be the entirety of a JPEG from an image at a border scanning thing when you come into the country and they take your photograph. That might be used as your unique ID, all of the bytes that make that up. So it could be several megabytes. When we go big, we tend to get some problems. So we quickly run into memory issues. We're going to run out of memory on a machine, storing all of these big IDs and having to keep them all around. We run into horizontal scaling issues as well. So imagine if I'm out there tagging my sheep and someone's barcode scanning them. That's great. if I have lots and lots of people doing that, and I'm feeding back into like a process that's using, say, a Python set in memory, I'm going to get a lot of contention for access to that, and I can't really scale that by adding more and more servers. I need to put it in some sort of data store so that we can, horizontally scale our application and have the data shared between it. Exact counting also gets expensive in a couple of ways. Number one being the space that you need for it. Even if we move it to a disk-based database, we'll have to store all of these things. And it also gets expensive in terms of retrieval time. So you want something that can do this quickly. You might want a fairly fast answer to have I seen this before. If you're doing something like fraud detection for a credit card company, if it takes a while to say, have I seen this before, and the customers just swipe their card somewhere and they're waiting for a purchase to go through, you've not got very long to respond to that. So you need to respond with preferably perfect accuracy, but we'll see why a decent amount of accuracy is useful sometimes. So we can use a database for this. And if you follow Marc-André's talk before, you will see that there are lots and lots of databases out of there. Lots and lots of them are perfectly valid for doing this sort of thing. We're going to focus on Redis, which it's coincidental but fortunate that this wasn't a database that was talked about much in the previous talk, so I don't get to bore you with more Redis stuff. It should be new. Redis falls into the key value store category of databases. So it doesn't have tables, it's generally schemaless, and you store things at a key, and you store a value there. So how does that relate to this picture behind me? The woman here is working in the Library of Congress in Washington, D.C. in the 70s, and she's using their index system, which is kind of like a sort of manual in-person Redis. So if you imagine each of those drawers is a unique storage location, and it has a label on it, and that label is the key. So every key is unique, and that's how she can find out which box she wants. Then you open up the box, and inside there, she's got a lot of index cards. So that looks to me like one of the Redis data types, which is a list or maybe a stream, and we'll see what other data types there are. So if you can think of Redis rather than as a table-based approach, it's more like a sort of large collection of boxes, each of which can contain different data types. This is the scary bit for database people. People think that Redis keeps all the data in memory. This is true. It does keep all of the data in memory. So if you pull the plug or reboot the server, what happens? Well, unless you've configured some persistence, and you have several options for that, then yeah, you'll lose all your data, which is why people think of Redis as a cache. It's ephemeral. It's something that makes other databases go faster. With appropriate persistence, you can absolutely use it as a primary database. And for our case, it's important that it's a network resource. So like other databases, you can connect to it. It lives on a host and a port, and you can use driver software, and we'll look at how that works in Python. And you can share the data amongst various applications, and it'll manage access to the data for you. So this is where I tend to do a little bit of a poll. So who here has used Redis? If you could just briefly put your hand up. Cool. Who's used Redis for a cache or a session store? This is where most of the hands go back up. Who's used Redis to do pub/sub, so publish, subscribe? Yep, quite a few. Who's used Redis to actually store primary data or do something else? Thank you. Part of our mission at Redis is to educate people that Redis can be trusted and used as a primary data store for all sorts of things. It surprises a lot of people that most of these data types exist. Most people would use the string, which is just caching, store any old binary string in there, tell us how long to remember it for, and then we'll conveniently forget it after a certain amount of time. And then you've got the basis of a cache. We're going to look today at the set for deduplicating items, and it behaves like a Python set. And we're going to look at the hyperloglog, which may be something new to you. We're also going to look at the Bloom filter, which doesn't appear here because it's an extra module for Redis that is available via a loadable modules interface. So these ones are built in out of the box. As you can see, there are other things. If you're interested in Redis streams, I have a workshop about that tomorrow. But it can also be used to store lists, geospatial data, bit fields if you want to be very compact about how you store things. A lot of people use it for sorted sets, which is like a set but has an associated score, and things are kept in rank order. So if you're a game that's sort of massively online, like the Rocket League game on the various consoles, you would use a sorted set to maintain your leaderboard, and you might show a slice through that for like, where am I and who are the players around me? So back to some code. So let's move our counting problem into Redis in one of the ways that we could do this. So Redis has a set data type. Python has a set data type. Redis has a Python driver. It should be a fairly easy lift and shift to move things. And it turns out it is. So here I'm just importing Redis Pi, which is the common Redis client or SDK for Redis for Python programmers. And I'm just saying, hey, go connect to Redis, and we can configure where it is. I'm just using the defaults. And we're basically saying, OK, delete anything at a key called sheep scene. And then we're saying, add some IDs to a key called sheep scene using a command or a function called sadd, which is set_add. Database people might here be a bit, well, hang on, don't you have to tell it that sheep scene is a set, and don't you have to allocate how much space you want for it? And the answer to that is no, it does that for you. So it doesn't really care about things like that. In some ways, it's very developer-friendly. Just be like, put something in there, use the appropriate command, it'll set up some storage, it'll set up the data type, don't worry about it. So we add things into the set there, and then at the bottom, we ask it, how many sheep have we seen, and we use the command scard. So cardinality is kind of a sort of techie word for how many things are in the set, what's the size of it. So the same way as we used len in Python, and we used we just put things into the set in Python, we can do that in Redis. It's very easy. And what we've solved here is one of our issues. So we now have some sort of horizontal scalability. So I could collect lots and lots of lots of instances of my scanning application to that same Redis. They'll put things in there, and Redis will figure it out and deduplicate anything, that someone scans the same sheep twice, two people scan the same sheep. We don't care. It will deduplicate that. So fairly simple. Then the other question we had was, well, OK, rather than how many identifiers are there, have I seen a specific identifier? And again, we've got similar code. I'm just doing some cleanup to delete an old set and then creating one with some values. I can put several in one command. And then in order to determine if I've seen something, I ask Redis, hey, is this thing a member of the set at a given key name? And if that key name contains a set, it'll come back with a true/false response. So we can say, yeah, we've seen that one before. Or no, we haven't seen that one before. And OK, right, that's great. We're done with Redis. So we've got 13 minutes left, no problems at all, right? So we've moved everything to a database. Databases are a panacea, our problem's solved. Going back to what I said about Redis, it keeps a copy of all the data in memory. So it does that so that it is very, very fast. It will also persist it. I'm going to keep saying Redis persists data. It is safe for that. But to keep a copy in memory, which is the way that it achieves performance, we obviously burn through a finite resource. So imagine these keys are JPEG images, because Redis can store binary data, or there's something much bigger than that, or we've got a lot of sheep, or both. Then we need to basically think about what we're doing here, because we can only go so big with memory. We can cluster Redis and shard the database and all of that stuff, but that's not the approach we're going to take. So what we're going to do here is make some trade-offs. So we make trade-offs quite a lot in computer programming, but what we're going to do here is lose some qualities and gain some others. And we're going to make an unusual trade-off. And what we're going to do is introduce the concept of a probabilistic data structure. So the set that we've used so far is what you would call a deterministic data structure. If I put 100 distinct things in, there's always going to be 100 in there. I can get them back out again. I can figure out what they are. It's never going to lie to me. It's always right. That comes at the cost of storage efficiency. So for some applications where we want to, for example, count things, but we don't need that absolute accuracy, we can start to make some trade-offs between accuracy and storage efficiency and a little bit functionality, but mostly between accuracy and storage efficiency. I'm going to look at a couple of what are called probabilistic data structures that do this. They basically work as a family by hashing or magicking the data away with hash functions, making it smaller. And then if you've worked with hashing before, you'll know that part of the deal with hashing is you can get conflicts. So sometimes you will get answers that aren't always correct. And we'll see why that might be a good thing. So we'll look at two things. So the set in Python and Redis we could use to answer both of our questions, which is how many distinct things have we seen, and have I seen this distinct thing? When we move to probabilistic data structures, they're a little bit more one-dimensional. They're optimized for one use case or another. So we're going to use two different ones. So I'm going to use a hyperloglog, which is a mathematical formula that is way above my pay grade. And it presents a similar interface to set, and it's optimized for counting. So what it does is it essentially hashes away all of the data into a long bit stream, and it actually does something with counting, I think, continuous numbers of zeros. But the takeaway is we're going to hash the data away, and one of the trade-offs here is we can't get that data back again. So if I put things in the set, the way I see if I've seen them before or if I need to update my counter is by hashing it and seeing if the bits in the data structure are already set according to how the algorithm wants them to be. So this isn't built into Python, so we could use a library for that, but it is a data type in Redis. So we're going to move all of that logic and that math into the database. And there are benefits and trade-offs here. So we're going to lose some accuracy. Why is that OK? Well, in some use cases, it's fine. So if I was a traffic camera, for example, and I wanted to see how many different vehicles have driven past me in a given day, I just need to know how many different license plates I've read. I don't need to know what they are. And if I'm in the ballpark range, then I'm OK. If I am, for example, counting votes in a social media poll or how many likes are on a tweet, if I can say there's like 17.4K likes in there and I can save a lot of memory because I'm doing this for every tweet in the system, it's a lot easier than maintaining a set of people who've liked it. So here's the algorithm. I'm going to skip straight past this because there's a lot of math and you should use the library. And we're going to look at some code again. So how do you use this? It's very, very simple. So we basically just tell Redis, we're going to do a comparison here. We're going to use the set and the hyperloglog. So hyperloglog commands begin PF after the mathematician who created them, Philippe Flageolet. We're going to add to both data structures and see what happens when we do that. So we use pf add, so add to a hyperloglog, pf count, how many are there? Then we're going to ask Redis, how much memory or RAM are you burning through to store each of these 100,000 IDs, and how many distinct ones do you have? So when we move this set into a hyperloglog, you'll see the set is right, as we'd expect, 100,000 sheep, but at the cost of 4.6 megabytes in RAM. So if I'm doing this per user on a massively multi-user system, or I'm doing it per tweet because I'm Twitter and I'm looking at likes, this gets really expensive. With the hyperloglog, we're slightly off. So we got 99,565, so we're a little bit out, but we only use 12K of RAM. So that's a big saving for a little bit of accuracy. So if we wanted to say there are 99.5 or 99.6K likes on this thing, then hyperloglog is great for that. So the other data structure that we need here is the one that answers the set membership question. So have I seen this sheep or this ID before? We're going to use something called a Bloom filter here. And what that does is I've got a visual representation of it here. It's a fun data structure to build. I've built one with a Raspberry Pi and LEDs, and there's a video of that on YouTube. We have a bit field, and mine isn't particularly wide because I have to fit it on the slide. We'd have a much wider one for reals. And we have a number of hash functions. And each hash function takes an ID or a string or some bit of data and turns it into a number between 0 and the size of the bit field. So we run the data through each of those hash functions, and we can tweak the size of the bit field and the number of hash functions. And what happens is we reduce it to like a few bits. So if I stored this ID, and it doesn't matter how long my ID is now, I've hashed it away to those 3 positions, and we set them to 1. And then I store another one, and that might hash to those 3 positions. We set them to 1. Then I store a third, and same thing. So how do I then look up if I've seen something before, if I don't have the data anymore? So what I do is I hash it and see what happens. And at the minute I don't get a 1 from one of my hash functions, I know it's not in there. And I can say with absolute certainty, 2045 is not in there. And then if I look for 9107, it hashes to 3 things, and they're all set to 1. So I can't say with certainty that they're in there, because we're talking about hashing, and we might have collisions. But I can say with a high degree of certainty, it might be in there. So we might have seen 9107. 2989 here also hashes to 3 positions. And as you can see, we don't have that anymore. We didn't put it in there. So that's a case of a false positive. So Redis Bloom is a component of something called Redis Stack, which is an extra module for Redis. It implements a Bloom filter, and again, it's very simple to work with. So unusually for Redis, there is a create step here, so we tell the Bloom filter how many things I think I might want to store and what my desired probability of error is. It then does the math to figure out how wide and how many hash functions. Then we basically just use it like a set. We do bloomfilter.add to put things in there, bloomfilter.exists for are they in there? But again, the answers now are no, they're not, absolute certainty, or yeah, it might be with a configurable degree of certainty. So the trade-off here is lots of space, some certainty. When should you use these? Basically, don't use them for like elections or anything serious where you're trying to count, has this voter voted before? Do use them for things where you want near approximation. So you've got an endless stream of data. We see people using them for fraud reasons. Social media. Have I read this article on a site like Medium before where, if you're a little bit wrong, it doesn't really matter? And that's it. I have some code which you're welcome to look at, and I'll make these available on Twitter. And if you want to try Redis, please do. I have a workshop tomorrow looking at Redis streams.
Thank you very much, Simon. Let's thank Simon. That was a great talk. The probabilistic data reminds me of a story about YouTube and how they update their view counts, because writing to a database is much more expensive than reading from it. And if you have to touch the database every time someone watches a video, that can be very expensive. So what they do is for very low counts of video watches, they keep an exact count. And then when you get beyond a certain threshold, there's a 1 in 10 chance that your view will add a number 10 to it. And then when it gets bigger, there's a 1 in 100 chance that your view will add 100. So it's approximately right, the view counts.
The other thing you can do with these, if you've got the algorithms, is you can take the state of that bit filter, which is very small, and drop it down into a browser. So if you're signing up new users and you've got unique usernames and they're banging away on your front end, you can save a lot of calls to a database by just right there in the browser querying this thing. And
That's a great idea.
You'll be wrong sometimes, but it's OK. It saves a lot of back end.
OK, do we have any questions for Simon?
Hello.
I have been working a lot with Redis of late, with streams, and but I find that in Redis for Python there are lesser or less flexible APIs available for streams. So is this a good information, or am I making some kind of
You should come to my streams workshop tomorrow because we're looking at Python. In short, Redis, the company, recently started helping out and maintaining several Redis clients that were built by the community in the past. So Andy, who ran Redis Pi, has worked with us, and we're now kind of working with it. So we've been working a lot on modernizing interfaces and keeping up with where the product is. So for Redis Pi, for example, we added async support recently, which I think deprecates AIO Redis, the other Redis client. So I don't know if that sort of answers your question, but that, and then in terms of the actual streams product, that's a really wide topic that I can talk about in my workshop tomorrow. But yeah, we are actively working on streams, commands, and functionality.
Okay, I think we're out of time, so no more questions. You can catch Andy afterwards or attend his workshop, which sounds great. Let's thank Andy again for his... Sorry, Simon.
Thank you.
Simon. Thank you.